So when we're talking about an unused bond, what are we actually talking about in an atom? Yeah? A valence electron, and specifically what type of valence electron? Are all of those electrons able to bond? Which ones are able to bond? The unpaired electrons. So when they say there's a bond ready to form, they mean there's an unpaired electron. So hydrogen has one unpaired electron. Okay? Because it has two what? Not two valence electrons, it has two unpaired electrons, yes. Okay, so on our page, it says number 1A on page 10, at room temperature, what happens when you place an oxygen molecule and a hydrogen molecule together in a box? What do the molecules do? There are three things. What are they? Tell your partner. What's one thing that they do? They move. And how do they move? They move in straight lines. What else do they do? Yes. They bounce off the walls and they bounce off each other. Okay. Okay. What did happen there? The particles moved faster, yes? Well, let's take a look. Let's see what happens. Okay, so what happens when you apply heat to the gases with a flame? What do the molecules do? They move faster, yes. So number one, they move faster. What's next? The bonds break. So the molecules move faster, the bonds break, and what happens next? New bonds form, and we form a water molecule. And I think we've already answered this, but why did the flame make a difference? The heat made the particles move faster. Now, when the particles collide with the walls or with each other, they... They what? They bounce faster. Well, you know what? I think we've got a slowed down picture of this, so let's just watch. Okay. What do? They break apart into atoms. Yes? It requires collision. Yeah. Yeah. And in fact, here they're saying it's okay if they collide with the walls, but quite frankly, usually that will just result in if the particles do break apart, the closest particle is who they were with before, so they'll probably just get back together. So usually for a collision to actually produce a reaction, it's a collision between two particles, right? So they collide, the electrons break apart, the atoms break apart, and then they will form a bond with a new partner. And when the atoms are on their own, they are free to do what? Bond to other atoms. At the end of the reaction, you have one water molecule that was made and one oxygen atom left over. Why can't the oxygen atom join up with the water molecule? Tell your partner what you think. What do you guys think? Why can't this oxygen atom over here, why can't it not get together with that water molecule? It doesn't have any leftover bonds. The water molecule, all the bonds are taken up, okay? Do you guys remember what IE means? Id, est, that is to say, in other words. Yes? I.e., in other words. In other words, the water molecule has no unpaired electrons. Ooh, here's a, yes, sorry. Yes. Both which? The oxygens?
Yeah, both oxygens.
You could, however, it is more stable for both hydrogens to be with one oxygen than for one hydrogen to be with. I mean, you could kind of. Ish.
That would be more fair.
It would be more fair, but sometimes life is not fair. And remember, we're looking at trillions and trillions and trillions of atoms. So, like, you know, yeah, most of them will find a partner. So back in the olden days, when we used to have more time in our classes, there were some Halloween demos that me and my former department head would do, and it involved creating hydrogen gas. So we would do a single replacement reaction. We would put zinc into acid, okay, and then the zinc would replace the H in the HCl, okay, so you would end up with zinc chloride and you get hydrogen gas made, and we would collect it in a balloon, and because H2 is lighter than air, it's less dense than air, we could then have the balloon on a string, and we'd take so the balloon's on a string, and we'd take one of these, and we'd tape a candle to it, and then I would do this little dramatic thing, because, you know, do you guys know about the Hindenburg blimp? Yeah? No? The Hindenburg blimp was one of the first lighter than air sort of floaty things, okay? So a blimp is basically just a thing like this with like this. It's almost like a hot air balloon, except for it's not hot air in here. And this is sealed. So blimps these days will have helium gas in them. But this one had hydrogen gas in it. And what happens if we apply a flame to hydrogen? Boom! So what happened was, so this blimp, the Hindenburg, was coming into New York Harbor. And apparently there was like some, I don't know, some like thing at the top of the building, and there was like a spark that went across from the building to the Hindenburg, and all of a sudden, boom, just like that. Anyway, so we would do the big boom. And then we would take the balloon that we'd create, another balloon that we'd put hydrogen into, and we'd get an oxygen canister because it's harder to generate oxygen. And so we'd fill up the rest of it with oxygen in a 2-to-1 ratio. ooh, look, a 2-to-1 ratio. And we would then light it off and it would go boom even louder, which was amazing. And one year, my department had decided that she was going to do this in the Commons. So she did it on the bridge. She had the balloon tied to the railing at the bridge, and she lit it off, and the whole building shook. All the glass in the Commons shook, and of course they're near the office, so all the admin came running out, like they were freaking out. They're like, what's going on? Anyway, so we weren't allowed to do that anymore. But I feel like maybe just before Christmas, maybe we can do that for you guys. Okay, we won't do like all the demos because they're exhausting and we don't really have time, but we'll work that one in, okay? Not all the demos are that exciting. And some of them require for people to carry cash, and nobody carries cash anymore. So, yeah. Anywho, so that was loud. Okay, so our next question then is, what do we end up with when we place 2 H2 molecules and 1 O2 molecule in a box and apply a flame? We end up with 2 H2O molecules. And if we were to write this as an equation, we would have 2 H2 molecules and we would have 1 O2 molecule. Do we write a coefficient of 1? No. And do I write an equal sign or an arrow? An arrow. And we would make 2 H2O. This would be H2 is a what state of matter? Gas. Oxygen is a gas. And what is water? Liquid. Okay? So how do we know that a reaction has taken place? How do we know that a chemical reaction has taken place? A new substance was formed and old substances were used up. Okay, you can fill that one in. Now, do you guys remember what we call the starting substances? Those are our reactants. Yes. Do you think that you could take this and draw what happens just after the flame is applied? What would that look like? Something like that? Just after. Yes, which is essentially what I drew, just a little bit different. Okay. And then you can flip the page if you're in a flippy book, and if you're not in a flippy book, then just stay where you are. What do we call those?
What?
The stuff at the end.
Product.
Products. Okay, so that's number 8. What do we call those? Those are products. Now, number 9, there's nothing for you to write down. It's just kind of there for you to refer to, but we're just going to watch the video for number 9. And I put like a during, right? We had our old bonds breaking, and then we have our new bonds forming. So if you look on our little picture there, the old bonds are breaking, the new bonds are forming, and then we end up with our product. Yay. Okay, and I don't know why I don't have a place for you to write down all of these. Maybe it's because we had them on page 3. On page 3, there's clues a chemical reaction change has taken place. It says appearance of bubbles, appearance of a cloudy substance, which is the precipitate. I did not write down bubbles of gas, and I did not write down new smell. If you want to write those down, you can take a moment and do so. Okay, so I will just pause that there. Yes?
Is it dissolving at physical terms?
We're going to talk about that in just a moment. I'm right with you there. Bubbles? What do you mean? What do I mean by bubbles? Oh, not on page 3, I don't think. Did I? Oh, okay. Yes, I did. Appearance of bubbles, and I missed new smell, and I missed a solid dissolving because, and we're going to talk about the solid dissolving. Okay, that's going to be question number 10 deals with a couple of issues. Okay, we good with that? Oh. Okay, we're going to talk about that in a minute because I want to go to here because we're going to deal with the fact, come on, that the video says solid dissolving is a sign of a chemical change. Yes? This is true only some of the time. Okay, so which of the following, we have two cases where solid dissolves. We have salt dissolving in water. NaCl solid goes to NaCl aqueous. We also have iron dissolving in acid. So we have iron solid. What does it become? Not just aqueous, but it becomes iron chloride aqueous. So it's no longer just iron, it's iron chloride. What's the charge of Fe in the reactants? +2? What does it say? Oh, if there is no charge, what is the charge? No charge. So if there's no charge, the charge is 0. Okay, and so what's going to happen is that it is going to become Fe2+, yes? And in the process, what's happening here is that Fe loses 2 electrons. Yeah? Well, where did those 2 electrons go? Have a chat with your neighbor about that. Where did those 2 electrons go? Chloride? We have, let's see, chloride. Cl over here is Cl minus, and chloride here is also Cl minus. So has the chloride accepted any electrons? Oh, and I forgot to put a 2 here, so there would be 2 chlorides and 2 hydrogens. Has the chloride changed the number of electrons from reactants to products? No, it goes from Cl minus to Cl minus. So we would have a Cl, which has a full valence shell, minus going to Cl minus. So nothing very exciting happening with the chloride. Who is changing? Hydrogen. Hydrogen is going from H+, yes? And then it becomes, what's the charge of hydrogen in the products? What does it say? 0. It says nothing, and if it says nothing, the charge is nothing. There is no charge. Okay, so the hydrogen goes from being +1 to being 0, and that happens to 2 hydrogen ions. So each H+ gains 1 electron. So the iron is losing 2 electrons. Each of the H's, each of the 2 H's gains 1 electron. So we have a gain of 2 electrons to offset the loss of 2 electrons. Yes? The iron gives them away to the 2 hydrogens. So back to our original question, which of the following is a chemical reaction, salt dissolving in water or iron dissolving in acid? Which is a chemical reaction? Number 1 or number 2? Number 2. This one is chemical. This one is physical. Okay? Now there's another one. The video lists bubbles of gas as a sign of a chemical change, but this is true only some of the time. Which of the following is a chemical reaction? What if we take baking soda and we mix it with vinegar and we get bubbles? Does that look like a chemical reaction or a physical reaction? Chemical. How about when water makes bubbles when heated on a stove? Physical. And that's why the best clue to whether there's been a chemical change or not is whether you have a new substance. Sometimes it's hard to tell just by looking at it, right? So there we are. And we go here and we go there. You can add heat, light, and noise to your list. If you're keeping a list, heat, light, and noise. Oh, I'm going to go back a little bit. Okay, so if the bonds, this is number 11, if the bonds in a reaction release energy, this energy goes into the surroundings and heats them up. What will the thermometer show? An increase in temperature. And a reaction that releases energy is called what? Exothermic, yes. Well, that's fun. It will show up later. If I write over it, it'll just show up again. A thermometer shows this as an increasing. I don't know what it's doing. It's crazy. I know. And the reaction is called exothermic. Okay, and I'm just going to close this. Oh my God. Okay. Okay, you guys can sort it out. It's fine. Oh, and just a little, no, that's, yeah. Okay, we're going to go back to the video. You guys can sort that last one out yourself because I think you probably already did. All right. Play. If a bonds absorb energy, this energy is pulled out of the surroundings and it cools them down. And what kind of reaction is this? Endothermic, yes. Okay, so we're going to see if it'll write this time. Pull, it does, that's good. Pulled out. A falling temperature. A reaction that absorbs energy is called endothermic. And I want to bring this to your attention because many students get confused because a reaction absorbs energy and the temperature goes down. And people don't like that. They're like, it's absorbing energy. The temperature must go up. But there's another step in there that they never mention to you. Okay? So it's sucking kinetic energy out of the surroundings. The reaction is sucking kinetic energy out of the surroundings. What is kinetic energy? Energy of movement, okay? So it takes this movement energy, so we're sucking movement energy out of the surroundings. We are absorbing it, but we're not just absorbing it, we are also turning it into stored energy. And that is the important bit is that now you no longer have as much kinetic energy because it has been transformed into potential energy. And if you don't have as much kinetic energy, what can you say about the speed of the molecules?
Slow.
They're moving slower. And if they're moving slower, what can you say about the temperature?
Low.
The temperature is lower. So when we say a reaction absorbs energy, it's not just absorbing energy, it's taking in kinetic energy and turning it into potential energy. And that's why the temperature drops. Sorry?
Does that mean like there's a signal in it's a right? So it's signaling.
It's
It's an increase in potential.
It's an increase in potential energy by taking kinetic energy from the surroundings and then turning it into potential energy, okay? Since the particles have less kinetic energy, they move slower and the temperature is lower. We will talk a lot more about this later because we have a whole section on thermochemistry. What do we call the energy required to break the bonds in the reactants? And that one is just a little preview of grade 12. That's on your previous page. The energy required to break the bonds is called the activation energy. So you remember how the hydrogen and oxygen just bounced off each other and did nothing until we applied the flame, the heat? That heat was the activation energy. It won't react without that additional input of energy. Okay, and that is it for this. So for the rest of class, you can study for your test. You can ask me for copies of the previous quizzes. I have some of them already. I will print off extras. I'm going to take a list here of who wants what. Well, not who wants what, but how many of which one. Yes?
Is it okay if I go talk?
Sure thing. Yeah. Hi. And you would like both quizzes? No, sorry. You have
The
something.
second one.
Just the second one. Sure. Okay. So I'm going to put down 1 for the second one. How many people want a copy of the second quiz?
Wow.
I'll just make 1 for everyone. Okay. 1 for everyone. Anyone want a copy of the first quiz?
Wait, are we allowed to format the test?
Huh?
Are we allowed to format?
Oh, the format of the test, there are 18 multiple choice questions, and then I think it's 5 or 6 written response questions.
Are response calculations or like?
Calculations. Other than the one where, guess what you need to describe? How to make a solution. Yes. Okay, so I'm going to make a bunch of copies of everything. Okay. And you're just here for copies? I'll get them to you in just a moment. Yes.
Test like tomorrow in flights.
Whoa.
Yeah. And don't forget, if you're going for Clubs Day, you can come in during Flex tomorrow, and I'll probably just give you like the multiple choice section to work on, and then you can do the written response in class, and then you won't need like extra time like after the thing. I'll be here by 8:15 tomorrow. Okay? Yeah.
Oh.
Okay, so if you want a copy of quiz number 1, I have them here. And I'll just go make copies of quiz number 2 because I've run out. It's the same, it's just on shorter paper.
Stop it. Oh my god.
No, that's the same one. Okay.
Yeah.